Okay, so we're going to finish up chapter 10, and we're going to finish up chapter 10 by looking into the significance test for the difference of means. So we did confidence intervals with the significance of confidence intervals with the difference of means. Now we're going to do the significance tests. And I want to reinforce that when you do significance tests, you need to make sure that you're writing with the null hypotheses and the alternative hypothesis. And then depending on your symbols, that you are also writing down what it means. So what is the mean of 1? Mean 1 is going to be the mean of what group? So you have to define what these things are. Because other words, people are going to be all like, I don't know where you got these numbers and I have no idea what you're talking about. So it's a good idea to go through those steps to go ahead and state what those hypotheses are. So significance test, we're looking for observed difference in sample means, can reflect an actual difference in the parameters, or it may be due to chance variation. So we're checking to see, is there really a difference, or is it just due to chance? Now the null hypothesis has a general form where the null is mean 1 minus mean 2 equals our hypothesized value. We are going to be using the hypothesized value as 0 because we're going to assume that there's no difference in the means. And so that means our new hypothesis is going to look like this. The mean 1 minus mean 2 is 0, or the mean 1 equals mean 2. And so the alternative hypothesis is going to be the difference that we expect. So it may be that mean 1 is greater than mean 2. It may be that mean 1 is less than mean 2. Or it may mean that they are just different from each other. So be careful about the way it's worded and how you state that alternative hypothesis. And then again, stating mean 1 stands for women, mean 2 stands for men, but stating which one is 1, which one is 2. So that way it's clear to everyone else that they know how you're setting up your hypothesis test. So the 2-sample t-test for the difference between two means. We're going to test the hypothesis of the difference in the mean blank, and the mean blank is 0 at a blank significance level. So again, that null hypothesis, did not mean to do that, sorry, I meant to grab the highlighter. That null hypothesis and that alternative hypothesis, depending on what you're looking for. And then stating what is the mean 1 and what is mean 2. And then we're going into the 2-sample t-test conditions. So we've got our random condition, our normal condition. And again, if our sample sizes are not greater than or equal to 30, it is our responsibility to graph both the samples. And then, of course, we have our independence condition. Now, if they have not already calculated your mean and standard deviation, that's the first thing you need to do. And we do that through a one-variable stats, if you did not remember. And then once you have that information, now we can calculate the t-statistic. So this is like a z-score, but really it's a t-score because our distribution is going to be a t-distribution. So we calculate this, and once we calculate that t-score, then we have to get the probability of getting that. So then we calculate a p-value, and we do that by a t-CDF. And do not forget using your degrees of freedom. The smaller sample size -1. And then you compare that to your significance level alpha. If it is less than alpha, we reject HO. If it is not less than alpha, we fail to reject HO. If we reject HO, we have convincing evidence of HA. If we fail to reject HO, then we do not have convincing evidence of HA. So we've got a sample problem, and in fact, doing this gave me an idea to do a science project with my daughter. So in commercials for Bounty paper products, the manufacturer claims that they are the quicker picker-upper, but they're also the stronger picker-upper. Are they stronger? Two AP Stat students, Wesley and Maverick, decided to find out. They selected a random sample of 30 Bounty paper towels and a random sample of 30 generic paper towels and measured their strength when wet. To do this, they uniformly soaked each paper towel with 4 ounces of water, held 2 opposite edges of the paper towel, and counted how many quarters each paper towel could hold until ripping alternating brands. Here are the results. So here's the results for Bounty. Because they are giving us straight up results, we're going to need to put that into our calculator under list 1. And then for generic, we have list 2. It definitely looks like Bounty has bigger numbers than the generic, but is it big enough of a difference, or could that have just happened by chance? So we will test the hypothesis that the difference between the mean number of quarters held by wet Bounty paper towels and wet generic paper towels is 0, with a 0.05. Let's play it. Let's put a 0.01 significance level. We always use 0.05. We're going to try a smaller significance level. There we go. Okay, so our null hypothesis is that there's no difference between the two. So I'm going to go ahead and say that the mean for Bounty is equal to the mean for the generic brand. Now we think, even before we gathered our data, that Bounty was stronger. So our mean for Bounty is greater than our mean for the generic. Now here is the part that a lot of people tend to forget. They tend to forget, what is mu b? Mu b is the mean amount of quarters held by Bounty paper towels. And then mu g is the mean amount of quarters held by generic paper towels. And it's really important to state what they mean so that way the reader understands what you're talking about. So now we're going to move on to our next thing. We're going to use a 2-sample t-test. Do not forget to name your test if the conditions are met. So random, yes, we had an SRS of 30 Bounty towels and an SRS of 30 generic towels. Why do I state that there were 30? Because I need that now for my normal. My normal condition is my sample size greater than or equal to 30? Well, yes, it is. But that only checks my Bounty. I also have to check my generic. So 30 is greater than or equal to 30. So we've met our normal condition for both samples. You have to check for both samples. Now independent. Reasonable to assume Bounty does not affect generic paper towels. So we're making sure the groups don't affect each other. And it's also reasonable to assume that there's more than 300 paper towels of each brand. So now it's time to move on. And before we can really move on, we need to calculate our information. So we need information for our Bounty. So we need an XB bar. So we're going to go to our calculator. We're going to calculate the one variable stats for Bounty. and we get a mean of 117.6 and a standard deviation of 6.6. Then we're going to look at generic. So we're going to have a mean of 88.1, and we're going to have a standard deviation of 6.3. Looks like quite the difference, but is it big enough? So now that we have that information, we're going to go ahead and calculate our t-value. So this is our t-score. So we subtract based on here. We're going to do bounty minus generic. So 117.6 minus 88.1 over our standard deviation formula, or standard error. So standard deviation of 1 squared divided by our sample size plus a standard deviation of another squared divided by our sample size. And this will give us that t-score. And so we end up with 29.5 divided by about 1.67, which gives us a t-value of 17.71. Now that we have that, we can go ahead and calculate our p-value. So what's the probability of getting a t-score like that? So what's the probability of getting a t-score? And then I'm going to come back up to here. Greater than, because of my symbol based on that HA, greater than 17.71. So this is going to be a t-CDF, because it's a t-distribution, with a lower bound of 17.71, an upper bound of something really high, so I'm going to go with 1,000, and degrees of freedom. Now, since both my sample sizes are 30, I can use just one of them and subtract 1. So I get degrees of freedom of 29. And when I get my answer looks kind of funny. It looks like this, 2.4 something or another, and then it says E negative 17. That is times 10 to the negative 17th power, which means it is really small. It is approximately 0, because there are 16 zeros before that 2, between the 2 and the decimal place. So this is definitely less than 0.01. So since our p-value is less than 0.01, we reject our null hypothesis, and we do have convincing evidence that wet bounty paper towels hold more quarters on average than wet generic paper towels. So we have evidence that they are the stronger picker-upper. Okay, so the next thing we're going to do is we're going to take a look at our calculators, which are really nice. They do a lot of stuff for us. And we're going to look at how to do this all on your calculator, so not how to break it apart. Now, it's important to know how to break it apart in step by step, because multiple choice questions will ask you to be able to set up all those formulas. And if you don't know how to do that, you're going to sink yourself on multiple choice questions. So it's important that you know how to set it up, but we can also check our answers. And in fact, it's preferred that we use the calculator version on the test. Why? Because when we calculate degrees of freedom here, there's a complicated formula for these degrees of freedom. And so the calculator will use the complicated formula rather than the safe way of our smallest sample minus 1. So what we're going to do is, luckily I calculated all of the one variable stat. So my data is already in the calculator. So let's take a look at this real quick. So here's my calculator. If I look at stat and edit, you can see that I have all those values in there already. Now to run the test, we're going to go to stat. We're going to go over to tests, and we're going to do a 2-sample t-test. Now our information is already in as data, so we're going to use data. List 1 is going to be for group 1. List 2 is for group 2. We want 1 of each number in there. And then our hypothesis, our alternative hypothesis, is that the bounty group, group 1, is going to be greater than the generic group. So we pick that. Now we don't do pooled data on t-tests. We only do them on z-tests. And then we hit calculate. And so all of this information here is the information. So we get a t-value of 17.6, really close to what we had, a p-value of 2.9 times 10 to the negative 25th, even smaller than what we had, with a degrees of freedom. Look at that degrees of freedom because of that special formula. The calculator can do that. And then it tells us our x-bars, our standard deviations, our sample size, everything. If you use the calculator, you have to not only write down what you typed into the calculator, but you have to write down all of the information. So you have to write down that we got a t-value of 17.64. We had a p-value of 2.98 times 10 to the negative 25th power. And then we had an x1 bar of 117.6. And we had a standard deviation of 6.64. And then we had x bar 2 was 88.13. And our standard deviation for group 2 was 6.3. And so there's all that stuff. What I haven't listed is what I put in the calculator. So 2 sample t-test with L1, L2, and then all that other information like mean 1 is greater than mean 2 was our alternative. And all of that information needs to be listed there for that. So it gives evidence that you know what you're doing and that you're doing it correctly. Okay, normal condition for 2 sample t procedures. Cannot state this enough. The more we go over it, the more likely you are to remember it. 2 sample t procedures are robust against non-normality, are more robust against non-normality than 1 sample t procedures. When the sizes of 2 samples are equal, the 2 populations being compared have distributions with similar shapes, then the probability values from the 2 tables are quite accurate. And in fact, they're as accurate as for the sample sizes as low as 5. Usually we don't like to go that low, but as long as they have the same sample size and they're similar shapes, it's going to be accurate as with a sample size as low as 5 for each group. Now, if the populations have different shapes, larger samples are needed. So guidelines for normal condition. If our sample size is less than 15, use 2 procedures, but if the data is clearly skewed or if there's outliers, don't use. Sample size 15 to 29. You can use unless there's outliers or strong skewness. Sample size 30 and up, it doesn't really matter. You can use it for skewed distributions or outliers. If you're planning your own study, choose equal sample sizes because it's going to decrease your standard error and making the power of your test higher. So always a good idea to try and make equal sample sizes if you can. Using t procedures wisely. So pooled 2 sample t procedures, do not use them. The only time we use the pooled sample is for proportions and only for significance test. So only for a z-test. So a 2 sample z-test. Not for the confidence interval, only for the significance test. Now, just a reminder of your inference for experiments. If you do random assignment with an experiment, then you can establish cause and effect. If you are doing a random sample from the population, then you can infer that to the larger population. So random sample from the population, then I could say, oh, this is how all of America feels. But if I do an experiment, which I usually have to have volunteers for, as long as I do a random assignment, then we can establish cause and effect. Please remember, do not use two-sample t-procedures on paired data. So this is our matched pairs experiment. That's when we go back and we calculate the differences first, and then we do a one-sample t-test on those differences. Beware of inference without randomness. So if you do not meet that random condition, you can't infer to the population or you can't establish cause and effect, which is really the whole purpose of doing our studies anyway. And that is it for Chapter 10.